Welcome to the WAN Technologies module. So far, we've learned about network models, protocol layering, and LAN technologies, specifically Ethernet technology. And in the last section, we learned about IP addressing, subnet masking, and routing IP packets through an Ethernet-based LAN. Now, in this section, we'll discuss how these companies interconnect their geographically dispersed LANs using different wide area network or WAN technologies. One key difference between a LAN and a WAN is that LANs are built, owned, and operated by individual companies and organizations. But unlike LANs, WANs are owned by third-party service providers. A company wanting to connect its geographically dispersed LANs must subscribe to a WAN service provider, such as a telephone company, to use or lease its WAN carrier network services. WAN service providers are also called service providers, telcos, WAN carriers, or just plain carriers. A company then uses the data links provided by these service providers to connect remote locations to each other or to access the internet. Like Ethernet LANs, traditional WAN protocols operate at the physical and data link layers, or layers 1 and 2. Each WAN technology, such as the point-to-point protocol or PPP or frame relay, uses a different layer 2 frame format and provides different options for reliability and error recovery. In this section, we'll also cover multi-protocol label switching, or MPLS, which isn't a WAN technology, but a WAN service offered by service providers. MPLS operates between Layer 2 and Layer 3, and some refer to MPLS as a Layer 2.5 protocol. Just as different Ethernet network devices such as hubs, bridges, and switches emerged to address specific network growth issues, WAN technologies also went through a similar evolution process. To explain these different WAN technologies, we'll revisit Acme Company and see how its growth required each different technology. If you've ever looked at a network diagram, you've probably seen a network cloud. This cloud typically represents the WAN, or the internet, through which data travels to get from one LAN to another. A cloud is used to represent the WAN, or internet, precisely because it's nebulous and hides the details of the service provider's network links and switching equipment. As a customer, you don't really need to know the exact path data takes through the provider's network to reach its final destination. In other words, data leaves one site, enters the cloud, and then somehow reaches the other. The path over which the data travels within the network cloud is the service provider's responsibility. But to understand WANs, you still need to be familiar with what happens within the cloud. Consider the network diagram shown on screen. In earlier sections, we discussed the LAN connectivity, the IP addressing scheme in use, and how data flowed between different LANs. We won't focus on the details of LANs anymore in this section, so we'll simplify our graphic. When we last saw them, Acme was getting the network at its manufacturing facility up and running. Of course, once the LAN at the new facility was working, Acme wanted to connect it to the LAN at its corporate headquarters. To accomplish this goal, the company installed a WAN link to interconnect the LANs at each location. Before we delve into the details of Acme Company's WAN, let's first discuss some of the equipment and terminology used in a WAN environment. Earlier, we saw that Acme installed a router to interconnect the different broadcast domains. Now the same router will interconnect Acme's geographically separated LANs. But to make this connection, Acme will also need to install additional equipment to connect its router to the service provider's network. Click each term to learn more. Customer Premises Equipment, or CPE, is any communications equipment located on the customer's premises that is used to connect to the service provider's network. The customer can own the CPE or can lease it from the service provider. Acme uses its CPE to connect to the service provider's nearest exchange or central office, often called a CO. A copper or fiber cable connects the CPE to the nearest CO. This cabling is often called the local loop or last mile. The device generating the data is known as Data Terminal Equipment, or DTE. In this case, the DTE is Acme's routers. The device that actually puts the data on the local loop is called Data Communications Equipment, or DCE. The DCE, such as a modem, ensures that the data is in the correct format for the local loop. Let's see what these components look like in a different context. A PC is another example of DTE that might also use a modem, the DCE, to access the local loop. The local loop can either be an analog line, like the voice-grade phone line coming into your home, or a digital line, like the ones used by companies. Earlier, we learned that computers generate digital signals, specifically ones and zeros. The analog phone line, however, typically carries voice traffic, which is a continuous series of electrical pulses that vary over time, like waves. A digital signal is like a light switch. It is either on or off. An analog signal is like a dimmer switch, which can vary. As you probably know from your home computer, to send computer data over an analog phone line, you need a modem. A modem converts or modulates the digital signal into a format for the analog phone line. At the other end, a modem converts or demodulates the analog signal into the digital signal a computer understands. Analog phone lines are typically copper. Routers also generate digital signals, but they usually connect to a digital line, so a modem isn't usually necessary. Instead, a router can use a CSU/DSU to connect to a digital line. CSU/DSU stands for Channel Service Unit and Digital Service Unit. Click the Additional Information button to learn more about CSU/DSU. CSU/DSU. A device called a CSU/DSU is required to prepare data traffic for digital lines. Network equipment manufacturers make CSUs and DSUs as separate physical devices or combined in a single physical device. Some manufacturers build the CSU/DSU into the WAN card inserted in the router. The CSU provides termination for the digital signal and ensures connection integrity through error correction and line monitoring. The DSU converts the digital frames used in the service provider's network into a frame format that the router can understand, and vice versa. Digital lines can either be copper or fiber. In fact, it is not the type of connection, copper or fiber, that dictates the type of line. Rather, it is the equipment being used on the line that dictates whether the line is analog or digital. After the data leaves the customer's location, it arrives at the service provider's central office. A CO is like a distribution center, sending data to other COs along the path to its final destination. Within any large city, a service provider might have several COs interconnected using high-speed fiber optic trunk lines. Some COs might connect to other service providers, such as international carriers. Within a central office, you'll find the different kind of switches that make this communication possible, some of which we'll cover later in this section. For now, the switches take the customer's data and send it to the correct location. Now that you know some of the terminology and concepts of WAN technology, let's take a look at the specific technologies used by WANs at Layer 1, the physical layer. Most people remember the days when traditional phone lines were used for both voice and data communications. Some of you might still use dial-up. In the old days, computers used modems to transmit digital data over these analog copper phone lines. And the fastest data transfer rate was only 30 kilobits per second. In this section, we're going to learn how WANs first went from using analog to digital phone lines, and then ultimately to fiber optic connections, providing ever-increasing bandwidth at the physical layer. You've probably heard the terms T1 and T3 or E1 and E3 in connection with WANs. Perhaps you have also heard of SONET or SDH. Let's take a look at what these terms mean, starting with T1. Unlike an analog or a plain old telephone service line, which is referred to as a POTS line, a T1 line is a high-speed digital telephone line that transfers data at 1.54 megabits per second. You might remember from the earlier section on bandwidth that 1.54 megabits per second isn't very fast by today's standards, but back when they were developed, they were lightning fast. T1 lines are dedicated connections between 2 points, as you see here, so they're also referred to as a point-to-point connection. T1 lines are used to transmit voice and data between devices in North America and Japan. The T in T1 comes from the term T-carrier system, a series of digital data transmission formats originally developed by the Bell system in the 1960s as a way to reduce the number of telephone cables in large cities. Originally designed for voice traffic, this system combines or multiplexes voice and data signals from different devices within a location into a single link using time division multiplexing, or TDM. With TDM, devices take turns transmitting a fixed amount of data across a link using a specific time slot or channel. A T1 line divides a single line into 24 different channels. You can think of a T1 line as a type of telephone service capable of transporting the equivalent of 24 conventional telephone lines over 2 pairs of wires. Instead of having individual phone lines for digital phones, fax machines, and computers, companies can use TDM and send all signals across a single T1 line. So how do you have 24 conversations occurring at the same time? To help explain this concept, let's look at a very simple TDM example. Here we have 3 devices wanting to share a single communications link. Each device is assigned a time slot from 1 to 3. Each device gets a turn to send data, and data from all 3 devices is placed into a single frame. So that data from each device is contained within its own time slot in each frame. The frame is sent, and then the process is repeated. If a device doesn't have any data to send, the time slot is left empty. Once transmitted, the data in each frame is sent to the corresponding time slot on the other end of the communications link. So, a T1 line consists of 24 channels, also known as time slots or DS0s, each operating at 64 kilobits per second. Each conversation, whether voice or data, is assigned to a specific time slot. Each time slot gets a turn to talk or transmit, 8 bits at a time. Once all 24 time slots have had a turn, a bit is stuffed in for framing and synchronization, and the process is repeated 8,000 times a second. So, if we do the math, we'll see that 24 time slots times 8 bits equals 192 bits. Add the extra bit we just mentioned, and you get 193 bits, which constitutes a single T1 frame. If this process happens 8,000 times per second, then a 193 multiplied by 8,000 times per second equals 1.54 megabits per second. As we just mentioned, a T1 line provides a customer with a dedicated connection from one location through the WAN carrier's network to a second location. Customers have a choice of allocating all of the time slots for data, or they can allocate all the time slots for voice, or they can allocate time slots for any combination of voice and data. Each of the time slots in the examples we've been looking at can also be referred to as a DS0. DS0 is the basic digital signaling rate. DS stands for digital signal and is a system of classifying digital circuits according to the rate and format of the signal. A DS0 offers 64 kilobits per second of bandwidth, the amount of bandwidth usually used for one telephone voice channel. A DS1 circuit is made up of 24 DS0s. You often hear people use the terms T1 and DS1 interchangeably, but technically speaking, they are not the same. The term DS1 refers to the digital signal service provided over the wire. A DS1 signal offers 1.54 megabits per second of bandwidth and has a specific format. It might be transported over a T1 line or another type of line. The term T1 refers to the physical line, which is copper wire, carrying a DS1 signal. If a DS1 circuit is transported over another type of material, such as fiber, it is no longer a T1.